next speaker is Sam Moffatt building scalable service driven web system
ครับก็เหมือนเดิมนะครับก็เดี๋ยว
ผมแปลให้ถ้าสงสัยหรือถ้ามีคำถามยังไงก็ถามได้นะครับ
ครับ
โอเคตบมือให้แซมด้วยครับ
ขอบคุณครับบุญดาสวัสดีครับ So I'm here to talk to you about scalable web systems. I have this nasty habit of wandering around, so please excuse that. Podiums and I don't get along. So a little bit of introduction to myself. I've done a lot of work in a few different areas. I started in local government. I moved on to the education sector. I worked for a small e-commerce company called eBay. They do a bit of business in Southeast Asia. I don't think there's a Thai site though, unfortunately. And these days I work for a company most people probably have never heard of called Sears. And we're a big retailer that's been around for about 125 years. And with each of these places, I've done a lot of work with a lot of technologies. I also worked as a core contributor to the Joomla project for many years. And now what I'm here to actually have a chat to you about is MongoDB, Storm, and Kafka. And looking at how we can use those three particular technologies with a bit of PHP to build a very scalable system. So what I want to do is walk back a little bit and think about how many web systems evolve. So if we look at your average web system, you start with a website. You run that on your own server, you have a database, and it's usually all sitting in one self-contained box. Because we're all very popular here, very quickly we decide that we need to have multiple servers, so the next choice is usually we put the database on a different server, and then we find out that we're really popular, and we have all of these servers, we create a pool, and then we go, well, wouldn't it be really awesome if we had a mobile app? So then you create an API server, your mobile app becomes very popular, you create even more API servers, and you start having all of these servers. And eventually, you end up with a model, hopefully, fingers crossed, everyone's doing well here, where you have all of these servers set up, and you use typically a sharding system, so that reads and writes go to the right place. Now, the great thing about this model is that for some types of data, it will scale up really nicely. But for other types of data, sharding isn't going to work well for you. If you look at Facebook and many of these other systems, you have lots of interrelated pieces of data that need to come together. So you take your set of servers that look really nice and neat here, and then something like this happens to them. Stuff is going all over the place, you've got reads all over the place, you've got writes happening all over the place, and it just starts looking ugly. And then the worst thing happens, you lose half of your servers, or a third of your servers in this case, and your entire cluster is now in pieces because writes aren't going where they're supposed to. So how do we solve this? Before we go into that, what I want to do is have a look at the CAP theorem. Who here has heard of the CAP theorem? Anyone? One person? Anyone else? Great. You can all be bored for the next 5 minutes learning about theory. So the CAP theorem consists of three sections: consistency, availability, and petition tolerance. And generally this is one of those, you've got three options, pick two. So let's see what our options are. Behind door number one, we have consistency. Consistency is the property that all of your clients see all of the current data, regardless of whether it's been updated, created, deleted at any given point in time. Consistency is usually what you use an RDBMS for, a database of some variety for, and that's usually a pretty popular choice. The next one is availability. So door number two gives you the ability to withstand individual systems going down. So in our example before, we had an entire cluster of our database servers go down. And the system fell over. So we would say that this is not necessarily an available system. And the last one's perhaps something that you don't normally see, and it's called partition tolerance. And that's a situation where as you grow up, you have more of these servers and they need to talk to each other. And if those servers, for whatever reason, can't keep talking to each other, then does the system fall over or does the system continue to work? So when you put these together, remember you've got a choice of two. The first choice is consistency and partition tolerance. And this is generally what an ACID database, RDBMS, will give you. So if you have a standard MySQL cluster set up, you can actually handle one of your MySQL clusters going down, and you still generally see all of the updates as they occurred, even though the two boxes can't talk to each other. The other option is consistency and availability. This is generally frowned upon because you end up with a split brain problem. And the problem is that you have a partition failure where one half of the cluster can't talk to the other half of the cluster. And both clusters think that they're the top dog. And they keep throwing updates. And eventually they start talking to each other and they realize, wait, you've changed this and you've changed this. Maybe there's a problem here. So, and that's called a split brain situation. And again, that's generally not where you want to be because it's very messy to recover from. And finally, the last option is availability and partition tolerance, which gives you what we call eventual consistency. So your data is not always the most up-to-date, which in a web system may or may not be good for you, but it is always available and it can handle half of the system not talking to each other. And what I want to go into is this last option here, and how we would build a system to handle that particular case. And what we're going to use is queues. Anyone familiar with the concept of queuing in computer systems? I should have translated. What's queue in Thai? Yeah, we come over.
Okay, to Sam, basically queuing in Thai is queue.
Queue.
Yeah, same thing.
Same.
Yeah,
Same?
Same.
Oh, well, queue. Same. So, now same. So what we're going to do is we're going to implement a queue, and instead of doing all of our writes live, instead of making all of our changes live, what we're going to do is put them in a queue. And what that means is that eventually the system will catch up, and that change will make it all the way through. This is a very simple way of implementing this model, but it's a very popular way. And if you've listened to Google over the years, you may have heard the word eventual consistency. A lot of their systems mean that, and a lot of the detractors say, well, that's actually just a weasel word for it. It should work at some point. So, in an architecture of this, we're going to build a very simple web application that takes messages, puts them in a queue, processes them, and then makes them available to the web app. So to build the web app, I'm going to use Angularjs and Bootstrap. Angularjs, for those who haven't heard of it, is a very popular JavaScript library. It's written by Google, and it with Bootstrap is becoming one of the de facto ways to build next generation web applications. Bootstrap is a Twitter project aimed at making the web look better, and it's a CSS library essentially that defines a bunch of HTML classes to define the look and feel of buttons and whatnot and make things very easy to scan. Now I'm going to plug that into a service backend I've written in Grigri. Grigri is a PHP framework very similar to the Joomla framework or platform or whatever it's called this month. It's much more service focused, which is why I've gone for it in this particular case. But it's essentially a PHP framework, and you could plug Joomla in, but in this particular example, I'm not doing that. I'm going to then use a Kafka server. Now Kafka, who here has heard of LinkedIn? LinkedIn, anyone know about LinkedIn? Yeah, a few people. So LinkedIn built Kafka because they found that the queue systems that were out there today, particularly ActiveMQ, didn't solve the problem for them. what would happen is that they would have these massive servers, it would create massive backlogs, and their systems were failing. So they built Kafka, which is essentially a log processing queue system where instead of having the server work out where all of the clients are, essentially the clients maintain the state, which is a really geeky way of saying it scales well. So this is a LinkedIn project, and they use it to do a lot of their stuff with analytics, data processing, and data mining. So the other project that is really useful here is Storm. Storm was a Twitter project that basically aims to do real-time message processing. It has a few other features such as continuous computation and distributed processing, but what we're going to use it for is message processing. Storm and Kafka work really well together because Storm keeps track of where it is in Kafka, and Kafka has the semantics to allow Storm to replay messages. So if our servers go down for whatever reason, we can hold all of that data in Kafka until everything else is back online. Once everything is online, then Storm processes it and puts it into whatever our data storage layer is. And in this case, I'm going to use MongoDB. We could have used anything else, but MongoDB is what I decided to use here. It could be MySQL if you want to use MySQL, but MongoDB it's a schemaless database, and allows me to very quickly prototype things, which is the choice here. And last but not least, Grigory then comes back into MongoDB to then process the reads as it goes out. So essentially our writes follow the arrows around the system, going all the way back to Grigory. Now, I'm not one for talking far too much, and I've already talked for a good 10 minutes now. So what I'm going to do is I'm going to give you a demo of this system in action. So do we want to hold here and do a translation of to date and then do the demo? Do translation? Yeah.
Okay, I'll translate first. Okay, ก็ก่อนที่แซมจะเดโมนะครับก็อย่างนี้แซมกำลังจะเดโมพูดถึงเรื่องตัวการสร้างเว็บให้มันสเกลได้เยอะๆนะครับเพราะฉะนั้นเนี่ยถ้าใครเจอปัญหาที่เกี่ยวกับเรื่องการทำเว็บขึ้นมาหนึ่งเว็บก็มันก็ดังขึ้นแล้วก็ดังขึ้นแล้วก็ใหญ่ขึ้นแล้วก็ใหญ่ขึ้นแล้วก็ต้องขยายระบบไปเรื่อยๆนะครับหลายคนก็จะมีปัญหาเพราะฉะนั้นเนี่ยวันนี้ที่แซมมาพูดก็เกี่ยวกับเรื่องการสเกลเว็บเป็นหลักนะครับซึ่งหลักๆของการสเกลเว็บเนี่ยแซมได้พูดเกี่ยวกับตัวทฤษฎีของ CAP นะฮะ CAP มันก็คือ CAP C คือ consistent A คือ availability ส่วน P ก็คือ partition tolerance นะฮะซึ่ง3ตัวเนี้ยมันจำเป็นที่จะต้องใช้เป็นทฤษฎีในการที่จะเอาไปพัฒนาตัวนี้นะฮะซึ่งหลักของ consistency เนี่ยเขาบอกว่า user อาจจะต้องเห็น data ตลอดเวลาไม่ว่า data มันจะถูกอัปเดตหรือเปล่าหรือทำอะไรอยู่ก็ตามนะครับเมื่อ user query data ในส่วนไหนก็ตามเขาจะต้องเห็น data ส่วน availability เนี่ยหมายถึงเมื่อระบบมันมีบางส่วนล่มไประบบมันจะต้องไม่ล่มไปด้วยนะครับถ้ามีส่วนใดส่วนหนึ่งหรือบางโหนดมันล่มไปมันต้องไม่ล่มส่วน partition tolerance เนี่ยหมายถึงว่าถ้าชิ้นที่มันใหญ่ขึ้นก็คือหมายถึงสมมติ network ล่มระหว่างโหนดหรือว่ามีระบบ message ล่มระหว่างโหนดระบบมันต้องไม่ล่มนะครับซึ่งตรงนี้เนี่ยเขาบอกว่าจุดหลักเนี่ยมันจะมีอยู่3ส่วนก็คือตัวการแก้ปัญหา C กับ P ก็คือถ้าเรา config database ให้ดีมันก็ไม่น่ามีปัญหาก็คือในตัว consistency กับ partition นะครับส่วน C กับ A ที่เป็น consistency กับ availability เนี่ยเขาบอกให้ใช้เทคนิคการ split brain ก็คือช่วยกันคิด2คนนะครับส่วนสุดท้ายเนี่ยคือเขาจะพูดถึงตัว message queuing ก็คือการเรียงลำดับของเรียกว่าคำสั่งที่จะเข้าไป process ในระบบแต่ละชิ้นก่อนที่มันจะออกมาอยู่ข้างนอกนะครับก็โดยภาพเมื่อกี้เนี่ยเขาพูดถึงว่าเขาแบ่งเซิร์ฟเวอร์ไว้ด้านหน้าส่วนหนึ่งที่ใช้ Angularjs แล้วก็ Bootstrap ที่เอาไว้ทำ UI มี Gris เป็น framework มี Kafka เป็นระบบ queue message นะครับมี Storm ที่เป็น real time message processing แล้วก็ MongoDB ที่เป็น database เดี๋ยวเขาเดโมให้ดูครับ back to you
You know what I love about translators is that they took the last 10 minutes of me speaking and turned it into about 2. So obviously I said too much or we're missing something in translation. Anyway, so, ooh, that looks a little fuzzy. Let's see if we can make that look a little better. Still fuzzy. Change the resolution. So what I want to do is I'm going to show you the bits and pieces of the code. Now I'm not going to actually expect anyone to read this. This is all actually online, and hopefully the slides will be online at some point. But what I want to do is show you how little work is required to get this sort of a model up and running. Optimize for VGA display. Let's see what that does. That looks a little, there we go. Look at that, we might even be able to read that. So here's my HTML file. So it's a very simple HTML file. And we'll just have a look at what that looks rendered. So that's our application. So it's a very simple network, social networking application. We're going to put Jom Social, Easy Social, all those wonderful social tools out of business with it. But what it allows you to do is do Twitter-like messaging. So live demos are scary. And the thing I want you to pick up from this is we have a little character counter on the right here. We've got our message box, and we're going to click New Message. And we've got our first problem. There's an entity quoting issue. Don't you just love live demos? Things always break. Anyway, so we can create a message, and we can create a reply. So we're going to create a little reply, and you'll notice as I'm typing, it's automatically updating that little character count on the right, and it's putting it in here. Now, if I type really quickly here, if I do this, and let's hit New Message and refresh really quickly, you'll notice that it appeared, and then as soon as I refreshed, it disappeared. If I refresh again, you'll notice that it's here again. So this is the eventual consistency portion. So as soon as I submitted it, my JavaScript application faked it, and if anyone's used Facebook a bit, you'll notice that they use this technique a lot, where you will type a message on Facebook, you hit send, and this little blue bar shows up about a second or so later next to the message that you've just sent. It's the same sort of principle where it hasn't actually committed that message that you've sent until that little blue bar appears. And early on with Facebook, you used to be able to do the exact same trick here, where if you refreshed quick enough, you would actually see that the message wasn't there. So that's a very quick demo of our application. As you can see, it only does 2 things: creates messages and creates replies. But the HTML for this is essentially this page. So we define a very simple scaffolding for the page. We import the Angularjs library and our application, and then we define the application as well as our views. Now the list view, a little bit more complicated, but still relatively simple. We have our form, for those who know that. We have a line, and then we just have a list with all of our messages, and then with all of our replies. So this is the entirety of the Angularjs application, and all of this functionality here in the UI is driven by JavaScript. We don't go back to PHP for this until we get the data. So if I have a look at the web inspector, let's move that over a little bit, and hopefully it doesn't crash. Let's reload the page. So we do a lot of requests, but at the very bottom here we have one request. And get rid of that, and move that over there. And basically this is a web service call. So we're using web services with our JavaScript application, and this web service could be anything. It could be a Joomla site, for example, and it has our message, live demos are scary, as well as the replies. And these 2 things are all that ties this application together. In terms of the user interface. So we're not going to PHP for anything but pulling data, writing data to the database and reading data from the database. All of the UI rendering, all of the templating happens automatically for us with Angularjs. So in the back end, we're writing to a MongoDB store. Let's do this. So if I run that, we can see that we have, in my messages database, 3 entries. So I have, at the start here, my message for the live demos is scary. It has my reply, and it also has, at the end, the second message that I wrote. This is a very simple schema. This could have mapped quite easily to MySQL, but in this case it's MongoDB, simply because it's very easy to add and remove fields or rename fields as I need them. And last but not least, we have the Storm component. So in the back end, we have 2 things. We have Kafka, and we can see here that we sent a message, and then we have Storm. So we sent 3 messages in this case. Let's make that a little bigger. So we can see that this is the data that we sent. So this is the data that the PHP application created, put on the queue. So we have the ID of this message a couple of times, the user ID, and the actual message itself, as well as some metadata about when it was created, and the parent ID. And then for the reply, the parent ID, instead of being empty, has some data in it. Very simple stuff. And then on the other side, we have Storm here. And what Storm is doing is it's reading then off Kafka and going, well, I need to commit these transactions and make some changes. So we have the debug out of Storm as it reads the messages and processes it across. And we can see all of our messages there as they come across the line. Now, the PHP for this is the bit of code that helps us write the message. So what we do is we get the data, the user ID, the message, a few other things. We validate that we actually have a message to send. We create a unique ID for this message so that we can track it throughout the system and then hand that ID back. And then this is both returned to the user in the request so that they get an acknowledgement that their message was processed somewhere. And then we use Kafka, this line here, to send it to Kafka. And if that has an error, we say there was an error. And then on the flip side, so we don't have any code for writing to MongoDB here, it's just for writing to Kafka. And then on the other side, we have, for when we want to get the messages, we have a bit of code that basically goes to MongoDB, finds the messages, and then basically grabs the replies and throws that back to the user. And last but not least, for the web stuff, we have, this is an Angularjs application, and this is all of the JavaScript that we use to power this particular app. So we add items, we reply to items, and we can actually edit the items if we wanted to, but I haven't built that. And then for the backing layer, all we have to do is tell it what the endpoint is. So this is the web service to use to create and edit messages, and Angularjs does the rest from there. Last but not least, this is the Storm topology. A lot of this is boilerplate, but basically all it's doing is saying connect to Kafka, and then create a new stream, and then with that stream what we're going to do is persist it, and then if we have a look at our persister, all it's doing, well, it's actually doing quite a lot, but what it's doing is then putting that data into MongoDB. Let's pull that across there. So it does a few things, make sure that the collection names operation, and then we issue an update to MongoDB. The great thing about this model is that because the IDs are consistent at ingest time, we can rerun this message safely as many times as it is needed without having to worry about multiple inserts with the same ID. And that, and last but not least, ooh, that looks really horrible. Retina display for an iPhone doesn't work so well. But let's go back to built-in display. See how that goes. Very good. And so last but not least, because this is very simple HTML, and because Bootstrap is already a responsive library, this already looks really nice when we have a look at it on an iOS device. So if I reload that, we have all of our messages nicely formatted, and it even, oops, oop, there we go. And it works. Reply. So because it's very simple JavaScript, 5 minutes, cool. It works really nicely. Now this is a HTML5 web application. This could have been any other sort of application that can very easily handle web services. And that, ladies and gentlemen, is the demo. So I'm going to leave that up there, and I think we're up to translators and time.
Okay. Is that the end of the presentation?
Yeah, we're all done.
Okay, so give a big round of
ขอได้ปรบมือครับ
Sam Moffatt โอเคครับก็เข้าเรื่องแปลอีกรอบ
เดโมเมื่อกี้นะครับ
อันนี้ไม่มีสไลด์ด้วยทำไงอ่ะ
We can redo the demo.
It's fine, it's fine. ก็เมื่อกี้เขาเดโมให้ดูนะครับคือปัญหาเวลาเกิดเนี่ยคือเวลาเรามีระบบที่มันใหญ่มากๆแล้วเวลามันมีคนส่งเมสเซจไปเยอะๆอะฮะถ้าปกติแล้วเนี่ยไอตัวเฟรมเวิร์กเรามันต่อดัตเตอร์เบสตรงๆเดี๋ยวมันก็จะมีปัญหาว่าดัตเตอร์เบสมันเขียนอ่านไม่ทันหรือถ้ามันมีคนพยายามที่ไป access ไอตัวเมสเซจเดียวกันน่ะคือฟิลเดียวกันใน ID ในดัตเตอร์เบสหลายๆคนพร้อมๆกันก็จะมีปัญหาว่าคนหนึ่งมันจะทำได้มั่งไม่ได้มั่งหรืออะไรอย่างนี้นะครับก็ทางออกของเขาก็เลยใช้ไอตัว Kafka ที่เป็น queuing message เพื่อ make sure คือไปทำทางอ้อมมาก่อนว่าไม่ว่า user จะไปพุทอะไรก็ตามไปกดอะไรใส่ก็ตามเนี่ยให้วิ่งไปที่คิวให้เขาไปเรียงคิวมาเพราะว่า user มี user จำนวนมากสามารถที่จะกด submit อะไรหลายๆอย่างพร้อมๆกันได้อย่างเมื่อกี้เขาลองโชว์ให้ดูครับคือถ้ากดปุ๊บคนนึง refresh คนนึง submit ถ้ากดเร็วๆเนี่ย message มันหายสังเกตนะครับว่า message มันจะตกหล่นอย่างเงี้ยพยานเนี่ยเขาบอกว่าเวลาส่ง message อย่างเงี้ยให้ไปที่คิวปุ๊บแล้วก็ไป process ที่คิวแล้วค่อยกลับมาที่ database ในกรณีนี้ไม่ว่า user จะมีกี่ร้อยกี่ล้านอยู่อีกฝั่งหนึ่งเวลาเขาส่ง message มามันจะไปถูกเรียงเข้ามาแล้วก็ database ก็จะไม่ถูกแบบกระหน่ำหรือว่าเขียนลงไปใน message เดียวกัน ID เดียวกันมันก็จะไม่ถูกเขียนทับในขณะที่คนนึงกำลังเขียนคนนึงกำลังอ่านมันก็จะไม่มีปัญหา database อะไรแบบประมาณนี้นะครับก็เมื่อกี้ที่โชว์แต่ส่วนโค้ดเนี่ยคิดว่าน่าจะมีอยู่ในเดโมอยู่แล้ว Sam could you please bring back the slide for them to download the demo or the demo
At the website?
Yeah the website
It's that.
ก็ถ้าสนใจนะครับก็โค้ดชุดนี้ดาวน์โหลดได้ตรงนี้แล้วก็ Sam are you available all day
I'm here all week.
Okay
I actually hit on Monday.
โอเคก็ถ้ามีปัญหาก็ถามแซมได้นะครับลองเอาโค้ดเข้าไปถามดูโอเค that's it